Alright, so today we're talking about the ideal gas law. And the ideal gas law is simply an equation that assumes that a gas is ideal. And if you remember back in your notes, an ideal gas is any gas that adheres to the 5 kind of tenets or 5 rules of kinetic molecular theory all the time. And the ideal gas law equation is really the only equation that has moles in it. Alright? So this is the form of the ideal gas law. PV equals N R T. Alright? And several things we already know. P is pressure, V is volume, and T is temperature. And we've been dealing with those pretty much for the last couple of weeks with just the gas laws. N is a little bit new, and N just stands for moles. Alright? We're familiar with moles from even a week before that. And then finally, R. And R is known as the ideal gas constant. And R has a value that doesn't change. That's why it's known as the ideal gas constant. And that value is 0.0821. Okay? It's a number you need to memorize for whenever we use our equation, which we usually call just PIV-NERT. Okay? This constant has these units, and it's a really strange unit, but it's liters times atmospheres divided by moles times Kelvin. Okay? So this comes about from this equation. So if we rearrange this equation to solve for R, so we have PV equals nRT. And if we want to get R by itself, we're going to divide both sides by NT. So really we have PV over NT equals R. Alright? And from that, I'm just going to put my PV values, PV and NT values, standard values. Okay? So pressure, standard pressure is 1 atm. Okay? The standard volume, if we have 1 mole of a gas, is 22.4 liters. And then standard moles, there's going to be 1 mole. And again, if you think back to standard temperature and pressure, standard temperature is 273 Kelvin. So if we take 1 times 22.4 and divide it by 1 times 273, we get the value 0.0821. And notice our units, our atmospheres, liters, all over moles Kelvin. Okay? So this value comes from our standard conditions for pressure, for volume, for moles, and for temperature. What will typically happen in questions like this is I will give you 4 of the variable, or 3 of the variables, and you have to solve for the 4th variable. Alright, so we're just going to do something kind of like this. What if I want to know what volume will a gas take up if its pressure is, we're going to do kind of a more difficult one. Let's say its pressure is 650 millimeters of mercury, and its moles are, let's just say, 3.5 moles, and the temperature is 58 degrees Celsius. Okay? So we are solving for volume. So a couple of ways we can do that. We can either rearrange our equation, kind of like we did up here. So if we know that PV equals nRT, how do we get V by itself? We're going to divide both sides by P. So if we divide both sides by P, P goes away over here, and volume really equals moles times R times T divided by P. The other way you can set this up, if you like to just solve for X, is we can just do P times X equals nRT, and then just plug your numbers in and solve for X. Okay? So either way, it doesn't really matter. I am going to do this first way though. So I can write my P back again that I just erased. Alright, so I need to put in moles, I need to put in temperature, and I need to put in pressure. Because our units for the ideal gas law are atmospheres, liters over moles Kelvin, though, I need to make sure my units for my the units that I put in match the units for the ideal gas law. So these units are incredibly important. So we need to ask ourselves, for my moles, is my unit in moles? And if we come down here to the bottom, we can see that yes, this is already in moles, right? What about my volume? Well, I don't know my volume, but whenever it comes out, I can be sure that my volume is going to be in liters, alright? Because up here, the ideal gas law, the volume part, is in liters. Alright, so the next two things I need to look at are, is my temperature in Kelvin? And it is not in Kelvin, so I need to change it to Kelvin. So I need to make sure I change that. And then lastly is my pressure in atmospheres, and it is not in atmospheres. So I also need to change my pressure from millimeters of mercury to atmospheres. So we're going to need a couple conversions first. So the first one is temperature, and that's fairly easy, because if we just add 273 to 58, we get Kelvin. So if we do that, we get 331 Kelvin. Alright? And then my pressure, I just need to come over, I'm just going to come to the bottom, and we're going to do just a quick fence and rail. So 650 mmHgs, and I want to convert them to atmospheres. So if mmHg is on the top, I want mmHg on the bottom, and I want to go to ATMs. 1 ATM equals 760 millimeters of mercury. So let me get my calculator real quick. So if we do 650 divided by 760, we get 0.855 atmospheres. 0.855 ATMs. Alright, so we are back up to our equation. So this is going to equal, our moles are 3.5 moles. Alright, our R is always the same, and it's 0.0821. My temperature in Kelvin is 331. And then lastly, my pressure in atmospheres is 0.855. Right, so again, we can get our calculator out, take 3.5 times 0.0821 times 331, and we're going to divide that by 0.855. We're going to see that our gas would take up 111 liters. Alright? So I can give you three variables, doesn't matter which three I give you, you can always solve for the fourth variable. Alright? Knowing the entire time that R is a constant, it always stays the same, and its value is 0.0821, and its units are liters, atmospheres, over moles Kelvin. Therefore your variables have to have units of liters, atmospheres, moles, and Kelvin.